Okay, let's look at the most well-known example of a system of physical laws, Isaac Newton's three laws of motion and his law of universal gravitation. Newton's laws of motion are supposed to apply to the motions of all bodies with mass that are subject to forces. Newton's first law, which is also known as the law of inertia, says that every object will maintain its state of motion unless acted upon by an outside force. So if an object is at rest, it'll remain at rest forever unless acted upon by an outside force. If an object is moving in a straight line at constant speed, it'll keep moving in a straight line at constant speed forever unless acted upon by an outside force. This tendency of a body to maintain a state of motion is called inertia. Newton's second law describes the relationship between force and mass and acceleration, when a net force does act on a body. Forces cause bodies to accelerate, to speed up, or slow down, or to change direction. The amount of acceleration is proportional to the force acting on the body and inversely proportional to the mass of the body. So if you push a body harder, it'll accelerate faster. And if a body is more massive, then you need to push it harder in order to accelerate it. Now, Newton's third law says that for every action, for every force applied on a body, there is an equal and opposite reaction. So if object A exerts a force on object B, then the third law says that object B also exerts an equal and opposite force on object A. So if I'm pushing against a wall and the wall's not moving, then the wall is pushing back on me with an equal and opposite force. These three laws are the core of the Newtonian framework for describing and predicting the motions of bodies through space under the influence of forces. To apply these laws, you still need a description of the forces acting on a body, but the three laws give you a recipe for calculating the motions of bodies once those forces are specified. Now, Newton famously added a fourth law, which describes a particular kind of force, the gravitational force. Newton's law of universal gravitation says that every massive body exerts a force of attraction on every other massive body in the whole universe. And it says that the strength of that attractive force between any two bodies is proportional to the product of their masses and inversely proportional to the distance between them. So the larger the masses, the stronger the attraction. The farther apart the masses are, the weaker the attraction. The letter G in the equation is just a constant of proportionality. It's there to make sure that the units are the same on both sides of the equal sign, and it's known as the gravitational constant. So Newton's three laws of motion, together with his law of universal gravitation, these are the defining laws of Newtonian mechanics. With these laws, you can describe the trajectory of a cannonball launched with a certain force in a certain direction. And when you develop the mathematics, you can predict the behavior of much more complex mechanical systems under the influence of various kinds of forces. Newton also famously applied these laws to create a successful predictive model of the motions of the planets around the sun. Today, we use the same laws to launch satellites into orbit around the Earth, navigate spacecraft that we send out into the solar system. So Newton's laws are the classic archetype of a universal law of nature. Now, before we move on, I'd like to introduce another set of famous laws that predate Newton's laws and that had a big influence on his work. These are Kepler's three laws of planetary motion. Prior to Kepler, the assumption was that the planets moved in perfect circular orbits, and Kepler actually bothered to calculate the orbits of the known planets from observational data and eventually came to accept that the planets move in elliptical orbits around the sun. So that is Kepler's first law of planetary motion. All planets move in elliptical orbits with the sun at one focus of the ellipse. Kepler's second law is known as the area law, and it says that as a planet moves around the sun in its orbit, it sweeps out equal areas in equal times. So this law describes how a planet speeds up as it gets closer to the sun and slows down as it gets farther away from the sun. The area law makes this precise. In any given unit of time, say a month, a planet will move some distance along its orbit. When it's farther away from the sun, it moves slower, and the distance it covers along its orbit is less than when it's close to the sun. But what is constant in any given unit of time is the area that is swept out by a line that connects the sun and the planet. So those two gray patches in the diagram have the same area. Now, Kepler's third law describes how the period of a planet, how long it takes to go around the sun, is related to its distance from the sun. The farther away a planet is, the longer its period. The Earth takes 365 days to go around the sun once. Mercury, the closest planet, only takes 88 days. Mars, which is farther out, takes 687 days, which is almost 2 Earth years to complete one orbit. And Saturn takes 30 years to complete one orbit. So Kepler's third law, again, makes this precise. It says that the square of the orbital period of a planet is proportional to the cube of the distance. Or more specifically, the cube of that distance A on the diagram, which is called the semi-major axis of its orbit, which isn't exactly the distance to the sun, but when these orbits are nearly circular, as they are, it's pretty close. And this relation holds for all the planets. In other words, if you square the year of each planet and divide it by the cube of its distance from the sun, you get the same number for all the planets. You can plot this, and all the planets line up right where they should. It even holds for the orbits of moons around a planet, like the moons of Jupiter. Now, this law, Kepler's third law, is known as the Harmonic Law, or sometimes called the Law of Harmonies. The reason for this is a bit obscure. It has to do with the belief that predates Kepler, but that Kepler held, that the spacing between the planets is somehow related to musical harmonies, which are ratios of frequencies of the pitches in a musical interval. So Kepler believed that God created the cosmos using principles of geometrical harmony, and that can be characterized by ratios like these. Now, to wrap up this introduction, I want to mention one final result. When Newton was developing his system of laws, he was aware of Kepler's laws. Kepler didn't have a theory to explain why his laws held. They did a good job describing the motions of the planets, but they didn't explain why the planets moved in this way. Now, Newton was actually able to prove that Kepler's laws follow as a matter of mathematical necessity from the assumption that the planets obey all of Newton's laws of motion and are subject to an inverse square law of attraction between the sun and each of the planets. This is one of many remarkable results that Newton was able to demonstrate within his, what he called, system of the world. Now, I'm mentioning this here partly because it's such an impressive achievement, but also because it'll be helpful to have this example in mind when we talk about a recurring question that we'll get to later about laws in science, which is whether or not laws are explanatory or merely descriptive. So let's move on now to talk about the different criteria that have been proposed to characterize laws in science.